Hi, everyone. Thank you for joining us. I'm Suzanne Simon with Restore America's Estuary. I am the program director for the NEP Coastal Watersheds Grants. I'm joined today by our Senior Manager of Communications, Rob Shane, who will be helping us out on the tech side of things. So you will hear his voice from time to time as well. We are very excited to spotlight two projects that were funded by this program. More on them in a minute, but I'll go through some housekeeping and general updates. Uh, as a housekeeping note, everyone is on mute. If you have a question or comment, please submit it via the control panel. Next slide, please. So I think most folks probably know who we are, but just in case, Restore America's Estuaries is dedicated to the protection of restoration of bays and estuaries as essential resources for our nation. You can see our 10 member groups there on the map. And then we also have a robust affiliate members program, and those folks are listed down below. If you are interested in joining, take a look at our website, which is www.estuaries.org for more information. Lots of great perks that come along with that. So make sure you check that out. Next slide, please. Okay, some resources and opportunities I wanted to highlight. All of these are available at our website, estuaries.org. Funding, always a big draw. Long Island Sound Community Impact Funds, those funds are, the LOIs are due December 1st. Those are folks in the Long Island Sound study area. The big news is the NEP Watersheds grants. They are out as of today. That is, the RFP is out today. Go again to Estuaries, hover over that grants and resources tab, scroll down to the NEP Watersheds grants. Key things to know is an informational webinar. The first one will be on November 29th. And LOIs are due January 26th. So by all means, check that out. For those of you in Southeast New England, there's their watershed implementation grants. That RFP will be out this spring. Some things to keep in mind a little bit further out. We have our big biennial summit in October of 2024. That's going to be in the DC metro area. So make sure you mark your calendars. And then, as always, we have National Estuaries Week each September. Two other resources I wanted to point out. The first is our restoration toolkit. The website is there. It's a great resource, especially for you and your partners that are just starting your restoration journey or looking for additional resources. The other one is our DEIJ initiative, which we call our Inclusive Coast Initiative. Lots of great information there as well. So that's just the tip of the iceberg. So be sure to go to our website. Next slide, please. So before we jump into the projects themselves, wanted to give a quick overview. So of the NEP Coastal Watersheds Grant Program. The NEP stands for National Estuary Program, which is a place-based program within the U.S. Environmental Protection Agency with the goal to protect and restore the water quality and ecological integrity of estuaries of national significance. Currently, there are 28 such estuaries along the Atlantic, Gulf, and Pacific coasts and Puerto Rico. EPA is a great website that provides more details. I encourage folks to learn more about that particular program. This grants program was established by Congress as a competitive fund designed to help coastal areas and to address urgent and challenging issues. Restore America's Estuaries administers the program in close coordination with and a big funding from EPA. So, a huge thank you to EPA for their financial support and ongoing partnership with this program. Similarly, a huge amount of gratitude to Congress and our partners who have helped make this program possible. Okay, next slide. Without further ado, I'll get to the good stuff. All right, first up is Russel Barsh, who is the director of Kwiaht, who will discuss the project in the San Juan Islands off the coast of Washington. Russell has been working on understanding and managing long-term human impacts on sailor sheet ecosystems for 50 years, from teaching at the University of Washington and advising treaty tribes in the 1970s to co-founding Kwiaht, a grassroots conservation laboratory in the San Juan Islands in 2006 with tribal leader and environmentalist Ken Hansen. Russell also worked with the United Nations agencies on grassroots ecological initiatives in Southern Africa and the Southwest Pacific. In recent years, his work has focused on changing food webs in the San Juan Islands and experiments in making key habitats more climate resilient. So with that, I will cede the floor to Russell. Take it away. Russell, you're on mute. You're on mute.
There we go. Okay. There we are. Okay. Let me just take us right into the slideshow and see if that's there yet. Great. Okay. And let's go to the first slide after that introductory one, show you where we are. We're in the very northwest corner of the United States on the Canadian border. In fact, we're a little closer to the capital of British Columbia than we are to the capital of our own state, Washington State, here in the San Juan Islands. And one of the things that I would underscore about this is that we're in that narrow band of the northern states of the United States that was glaciated in the last major um, Wisconsin glaciation episode, which means that our landscapes are only about 10 to 12,000 years old. This creates very different shorelines, very different geomorphology than you encounter further south in areas that have been shaped by much, much longer term forces and represent hundreds of thousands of years of shoreline change rather than a few thousand years of shoreline change. More of that in a moment, but it does shape the way our shorelines work, the way our ecosystems work, and how we think best we can intervene to protect our most valuable cultural and biological resources. Let's move on to the next slide, which shows our project site, Fisherman Bay on Lopez Island, as it was when I first took a look at it 50 years ago. And it's changed a bit. This is a nice introduction because you get a sense of how much of the bay is salt marsh, low-lying, sandy beaches, mud flats. It is a couple of miles around, but very shallow. It's again a post-glacial um, structure that is essentially a flooded area between two islands and only about 15 to 20 feet deep. On the other hand, it's been of enormous biological and cultural significance over the millennia that it's existed, and was in fact a major center of salmon and herring fishing, continues to be a major center of crab trapping, and of course, because of its salt marshes and beaches, an important area for shorebirds. Let's move on and take a look at some of those special resources that we have. Upper left hand, that's a core. It's from one of the huge indigenous villages that existed historically on the bay. Much of the bay has archaeological material, in fact, almost continuously around the edge of the bay, with a big village in the area that now has a small town, a business center in it. Archaeological material turns up everywhere. And of course, that's one of the things that's both a limitation on what we can do in terms of ground disturbance or construction, but also it's one of the resources that we may lose if we don't manage to stabilize shorelines as we deal with increasingly stormy winters and rising seas. Yellow sand verbena that hosts the critically endangered sand verbena moth, which we have in the San Juan Islands, and Henderson's checker mallow, a beautiful wildflower. Fisherman Bay is the only place in the San Juan Islands where it grows. And of course, lots of shorebirds, biggest shorebird concentration. And we've been monitoring shorebirds in Fisherman Bay since 2010. So that's our basic reference point for changes in the bay ecosystem, is the birds. It's something that we will continue to do working with local volunteers, and gives us a good sense of how well the bay is supporting not only the local ecosystem, but the surrounding islands. Let's move on. Next slide. Of course, like everywhere else, we are experiencing significant changes in our relationship with the sea, and our shorelines are now almost annually flooded during the winter. This is one of our main roads going under the water last year. And with rising seas and significantly stormier winters, which we're defining as more days that the winds go over 60 miles an hour. This increases all of the erosive forces applied to beaches, salt marshes, and other shoreline habitats around Fisherman Bay and elsewhere around the island. Let's move on. Here's encapsulated in a single picture is what we're dealing with. It shows you both the interesting geology as well as the limitations on our ability to, as it were, to rebuild the built environment. There are homes all around the bay. Here are some homes that are typically right on the edge of the back beach. Towards the viewer, from your perspective, you see this beautiful Salicornia or pickleweed marsh. We have hundreds of acres of pickleweed marsh around Fisherman Bay. That's a major habitat for shorebirds, for small crabs. When it's inundated, when the tides are up, that's where small fish go. This is our key current ecological resource in the bay. But you can see in this picture that it's breaking down. You can also see that the salt marsh is actually a very thin carpet over a gravel foundation. The gravel foundation is glacial outwash gravels. So that foundation was laid down no more than 14,000 years ago. And the Salicornia has developed since then. So we're dealing with a system, with a biological system that lies as a carpet over relatively recent gravels and is being peeled back, as it were, by our stormier winters and tides. Let's move on to the next slide, which shows you a better look at the Salicornia. It's not just a mat of living Salicornia. It's been there for thousands of years. So at this point, it's a layer of peat. So there's more like what you'd expect in freshwater systems to see in a fen, for example, with a thin, continuous carpet of peat underneath the living surface, lying on in contact with some kind of a foundation, which in a fen might be clay, and here it's gravel. 6 inches deep where you're looking at it here. It's at one end of the bay, but there are parts of the bay where the Salicornia that's alive today, the living salt marsh, is on about 2 to 3 feet of accumulated Salicornia peat. Now, when we started working on this, what struck us was that this material doesn't erode the same way that, say, a sandy bluff or a beach erodes. It is more knit together. It's organic material that, if you break it down as we have in our lab, is about 80% very fine sand held together by dead plant fibers. So it's a classic peat in terms of the dead plants, but it's holding a huge amount of sediment. And so as it deteriorates, as it decays, it's releasing that sediment. Let's move on to the next slide, which is an effort to describe this in graphic terms. The Salicornia peat is porous as a peat, so it absorbs water from precipitation, but also from the tides. When it rains, the peat fills with water, it saturates. When the tide comes up, it saturates. When the tide goes out, when rainwater drains out of the system, the peat expands, contracts, and slides. And as it slides towards the middle of the bay, it slides downhill into the bay, it breaks up prismatically. So if you want an analogy for the way this shoreline responds to seasonal storminess and to sea level rise, it's like glaciers. It's like the glaciers you may have seen or may have experience with in Alaska on the shoreline, which are slowly sliding into the ocean and breaking up into big blocks. Except here, it's peat rather than ice, and it's on a very small scale because these blocks are big enough for a burly human to pick up. But as those blocks decay, the fine sand in them, again, it's about 80% of their mass, just gets washed into the bottom of the bay. So the bay is filling up with fine sand, entombing the existing structure in the bottom of the bay, and at the same time destroying our salt marshes, which are rapidly disappearing through this process. So we tackled this from a point of view of what can we do? And existing models, the existing approaches here in Washington State to dealing with shoreline erosion didn't apply. Let's take a look at those in the next slide, because the existing models have prevailed ever since I started working on shoreline ecosystems here 25 years ago. And that is that we're preoccupied in the Salish Sea region of Washington State with the relationship between bluffs, shoreline bluffs, and beaches. The transport of sediment by literal erosion, by the drift of tides across the face of the shoreline, moving sands, moving sediments from the bases of shore bluffs onto beaches. And for many years, work on erosion here in the Salish Sea region was preoccupied with ensuring that we didn't interfere with that process of erosion because it's necessary to feed and maintain beaches. We're not talking about vegetation now. We're just talking about structure, geomorphological structure. Now, as a result of that, the solution that has been adopted with increasing confidence here in the Pacific Northwest for shoreline erosion, let's go to the next slide, is something that is called beach nourishment. If the bluff doesn't provide enough sand to maintain the beach, we simply import the sand from somewhere else and we put it on the beach. So it's simply an artificial replication of the natural process, which could be, say, used to accelerate or to make up for a deceleration or diversion of the natural process of sediment drift along shorelines. And that all works very well, except for two things. One is that because the active processes of erosion continue, and in fact, they're getting stronger, that you have to add material every 10 years or so. 25 years ago, this was every 20 years. Now it's every 10 years because things are speeding up. So it is an artificial process that is extremely expensive in the long term. And it has one very big additional flaw, which is what you do when sea levels rise. Let's go to the next slide. Down the bottom there in the next slide, you see I've put in a blue arrow at another line. What happens when sea levels get higher than the beaches that you have been adding material to in order to stabilize them, prevent them from completely washing away? And mind you, the kinds of habitats that we've been talking about, salt marshes, back beach habitats, are just above the beach nourishment boundary. So they are getting flooded, and beach nourishment can't stop that unless you accelerate it to a point that you're building levees that are higher than the highest tides of the year. And that has its own problems, engineering feasibility being definitely one of them. So we approach this from a totally different angle. We'll go to the next slide. Instead of thinking about how do we preserve what's there, we took a look at our Salicornia marshes. So again, back in the upper right-hand corner here, you see that it's breaking up, and we're looking at it, there's nowhere for it to go. If we slow erosion down, we're still going to lose the salt marsh because sea levels are rising and there's nowhere for the marsh to expand to migrate to further uphill. In fact, most of it is people's homes and roads and its structures. So without removing all of the human built structure, there's definitely nowhere to go. And actually, the topography also makes that impossible. Typically, the beaches and the back beach extend right to the rocks. So we are in a shrinking shoreline that we really can't, in the long term, with sea level rise, we can't preserve. On the other hand, that shoreline is emitting huge amounts of sediment into the bay and filling it up. And the issue that we raised for an experimental project, which is what this is what if we trapped that sediment and did something else with it? What if the deteriorating salt marsh could be used to build shoals in the bay that recreated the structure that was lost from earlier erosion? So taking a biological habitat structure above the average tides and turning it into a new kind of biological structure like shellfish beds that would be high quality habitat that might survive another century or two. So let's take a look at how that actually works. The first thing we did, of course, next slide, please. The first thing that we did was to experiment with just the numbers. If we planted shellfish beds, which species under what conditions would give us the necessary golden balance, the optimum between trapping sediment and growing fast enough as a biological structure to stay a little bit ahead of the sediment accumulation. Because if your shellfish don't grow fast enough, they'll simply be entombed in the sediment that they're trapping, and then you'll end up with no structure and you're back to the beginning. You want to have a shellfish complex which builds structure that stays a little bit ahead of the erosion and sediment trapping that that structure will do along shorelines. And so we did experiment. We gave it about 7 years to see what would happen, and we were able to satisfy ourselves that Pacific oysters, which is the typical commercial oyster of the West Coast, that Pacific oysters in this bay, under these circumstances, the way we set them up, were able to grow about twice as fast as they accumulated sediment. So that gives us that possibility of building living shoals that continue to grow as they get bigger and trap more sediment. Let's move on. Let's just talk about a little bit the practicalities of this. First thing we had to do is figure out where to put them. We chose 5 project sites around Fisherman Bay, adding up to about a quarter of a mile of shoreline, but in 5 different places with somewhat different conditions, because again, this was experimental. We wanted to learn something from this. The next thing was to go in and to map the topography of the tide flats in sufficient detail that we could figure out where the topography gave us opportunities to work with the bay bottom and the tides with shellfish beds. And so this is drone photography stitched together by a software package called Pix4D. So this is very fine scale, the 1 centimeter scale drone photography of the bay bottom on a -3 tide, so that we really could look at exactly what kind of surface the tides are moving through and sediments are moving across. Next slide, please. From that, we built our own topographic maps of the bay bottom, This is one from the upper part of the bay where there's a little bit of a hook right near the channel that connects the bay to San Juan Channel. And you can see there are topographic lines in there, which are inferred, they're DEMs, and also a little scrawly S in there, which is where our landscape architect decided, based on his modeling, we could squeeze in a structure that would help enclose that area and build it into a shellfish lagoon by closing in the space between two natural existing sandbars. So that's the way we looked at this, was to do these studies as, okay, where could we, if we could get something to grow, where would it have an impact on the recreation of good quality habitats? Let's move on to the next here so we can take a look at the nuts and bolts part of the process. We had to do this simply and cheaply, and we wanted to use all natural biodegradable materials. So we stitched our own burlap bags and filled them with dry culch, with dead oyster shell, of which there's a great deal around the Salish Sea because of oyster growing, commercial oyster growing. So stitching and filling burlap bags, and these formed the bricks that we used to build our structures initially. Let's take a look at the next slide where you can see hand placing of those bricks. And this is the S structure that you saw in the topographic map being constructed on the tide flat just by a few people with these 7,500-pound bags of shell. This creates the foundation into which, next slide, we were able to seed our little Pacific oysters, and we grew them working with Taylor Shellfish, one of the larger commercial growers. We grew our seed up to about a ½ inch in size, which was good for high survival, nice, tough little 6-month-old oysters that we seeded right into the bags and then left so that over the first winter, the bags decayed, the shells evened out into a nice foundation like a road, and the little ones grew at a rate which, of course, this part of the experiment was figuring out what survival and growth would actually look like when we had scaled up to structures of this size. Take a look at the next slide where we get to what these actually looked like when in place. This is one of the sites. You can see there are 3 structures in here. This is just after the bags were placed. This is actually interesting because it's the biggest and most intact of the salt marshes around Fisherman Bay. Several acres, partly privately owned, partly owned by the county as part of the county land banks preserve system, and rapidly deteriorating. This site is interesting because $250,000 was spent on beach nourishment here, and it's failed. And we spent about, I guess it would work out to maybe $5,000 on putting a structure in to try to trap sediments and prevent that salt marsh from simply disappearing and producing nothing but mud at the bottom of the bay. Next slide. This was a multi-year project, of course. We came back a year later, which was last summer, and took a look to see what was happening. Measuring growth and survival, which was good. Survival about 25 to 30%. Growth, many of the oysters doubled their size. So we got the kinds of results we had calculated we needed for these structures to stay ahead of both sea level rise and sediment accumulation. And that also, last slide, also gave us an opportunity to do some repairs along the shorelines where we were working and put in some more native vegetation, slow down erosion a little bit on the shore side, so that we're now working with homeowners to deal with their shoreline native vegetation, better stabilization, better salt tolerance at the same time that their living breakwaters are growing. So that was the plan, and we'll be continuing. Next slide. I think this is the last one coming up, because this is what it's all about. Since we are using birds, we'll be monitoring, continuing our now 15-year-long bird monitoring at 7 stations around the bay, several of which are breakwater sites as well, and see how the bird community responds to the shift in habitat from salt marshes into shoals. And we expect to see biomass shifts, species shifts, but overall, hopefully, retention of overall diversity and integrity of the bird community as an indicator that this may be working. So that's it. And acknowledgments to all, including our local team, and of course to the EPA. We're delighted to be able to do experiments like this.
Great. Thank you, Russell. All right. So like I said, we're going to save Q&A and discussion for a little bit later. So now, without further ado, I'd like to introduce Tom Ford, who is the director of the Santa Monica Bay National Estuary Program. And he will be talking about their eelgrass project off the coast of Southern California. Tom has spent the past 25 years working on coastal management in Los Angeles, California. He has worked to protect, enhance, and restore coastal wetlands, beaches, kelp forests, and most recently, offshore eelgrass. These efforts have required broad partnerships, applied science, communications, and development. Tom currently serves as the CEO of the Bay Foundation, director of the Santa Monica Bay National Estuary Program, co-executive director, there we go, of the Coastal Research Institute at Loyola Marymount University. Tom, take it away.
Thank you, Suzanne. And just quick time check, Suzanne, how long would you like me to go?
20 minutes if you'd like. Okay,
very good. Thank you. All right. So let's get going with the show. All right. So for many years, working in coastal ecosystems, located in an urbanized area of Los Angeles and Southern California, lots and lots of presentations that I attended at conferences over the years about eelgrass work, and I always felt left out. I was like, I don't think we have any. We don't have any work to do with eelgrass. It turns out that I was wrong, and that we have 2 species of eelgrass that persist off of our coast in Southern California and out on, notably, out on the Channel Islands off of Southern California. Zostera marina, which many folks are very familiar with, and Zostera pacifica, which many folks are not familiar with. This is a wider bladed species, and we've found it growing at depths of close to 70 feet, especially off of Catalina Island. It's known to persist at those similar depths elsewhere offshore. The focus of this work was to see if transplant methods that had been developed and used successfully with Zostera marina in more protected waters could work with Zostera pacifica in these more open coastal settings where we see, certainly larger, more frequent wave events and wave energy interacting with this species. And when it came to how this tied in with this grant opportunity, we were looking to see if we could get that habitat back, that we could, helpfully put back a vibrant community that was going to support fisheries. The other, benefits of eelgrass beds often being improved water quality, sediment retention, and a few other notable ecosystem services, including carbon sequestration. Long story short was we didn't have a very robust baseline as to how much or what species of grass was in our bay historically. We've certainly seen a tremendous amount of development along our coastline, which has altered the flux of nutrients, sediment. So not everything was kind of up in the air as to what had been changed, and we were trying to see if we could figure out where this grass could grow as part of our approach to our comprehensive management for our bay. And on this title slide here, we've got the Santa Monica Bay National Estuary Program, our key partners in this being the POWA Marine Research Group, the EPA, California State Coastal Conservancy, the National Estuary Program, and certainly Restore America's Estuaries. So appreciate everybody's efforts to help make this come through. And that image in the back is a giant black sea bass. This was a relatively small one, probably only a meter and a half in length. They're impressive fish to be around. Next slide, please. And Rob, if you wouldn't mind, I think we've got an animation game going. Keep going. There's a few more bullets on that slide, please. Appreciate it. All right. So here's a bit of the layout of the area in which we're working. The map shows you coastal Los Angeles County, which includes Catalina Island, which is in the lower portion of that map. And you see a couple different colored dots indicating the places where we had found and mapped eelgrass beds persisting off what we would call the backside, the sort of the windward side of Catalina Island, and then 3 potential transplant sites located in Santa Monica Bay itself, which are in those sort of aquamarine colors. So those sites, which you'll see a few times in some of the preliminary data I'll share later on, off of Dockweiler Beach, Redondo Beach, and Malaga Cove, for those of you that are familiar with the area. And we were trying to find corresponding characteristics where looking at where these grasses were persisting off of Catalina Island, and trying to find similar sites where it may persist then once transferred into Santa Monica Bay. Next slide, please. So here's some of the work that we were doing. Thanks again, Rob, for all the button pushing. So we looked at 2 methods that we selected. We're working with single shoot out plants. So we would take a small length of rhizome, maybe 2 centimeters, 3 centimeters in length, and using a landscaping staple, quick excavate a hole in the substrate, place that rhizome and the turion, and pin that down into the sand, kind of backfill it a little bit with our hand underwater. And then the other method that we used was a bundle shoot method, where we would take about 10 of those. I think we just switched our view. I'm not sure. About 10 of those turions. We lassoed a piece of hemp rope around them, used a tongue depressor, and then excavated a hole with our hands again, and placed that tongue depressor parallel with the surface of the substrate, maybe 5 to 10 centimeters deep, and that served a bit as an anchor for that bundle shoot. Both of these methods having been used by many practitioners around the globe successfully with Marina, and we were giving it a try out there in the open water with, again, Zostra pacifica. Next slide, please. All right. Thanks, Rob. So what we're looking at is also concordant monitoring activities. So we went and swam transects along these donor sites as well as these transplant sites, and then we were collecting the material out of those beds off of Catalina Island. We were able to transplant 500 turions into each one of our 3 transplant locations in Santa Monica Bay. We were also deploying sensors to take long-term data on temperature, wave characterization, light, and dissolved oxygen, and to assess changes in the community and or the condition of the outplants, or I should say transplants, sorry, transplants at 24 hours, 1 week, 2 weeks, 1 month, and then quarterly thereafter, to try to get an understanding of whether or not we were having success or not. Next slide, please. So here's a bit of what the work looked like. A through F on the screen. This is one of the divers ascending back to the surface with a game bag full of the rhizomes and turions. In the center top of the screen, you're looking at a melamine jig, basically a cutting board that was notched in order to help us organize the material and then bring that material down to the bottom. In the upper right corner, you see folks using that single shoot method, transplanting that grass. Lower left corner, there's just a shot from above, getting a look at some of the scale of the work and how we had laid out the transplants to better track them over time. And in the middle frame on the bottom, we've got a nice octopus bimaculoides finding some refuge, or maybe just being curious, hanging out in a brand new planted bundle. And then you can see the sand anchor in the lower right corner that's used to, in this case, support one of the pressure sensors that we're using to help interpret wave characterization. Next slide, please. Here's just a few more images of what things looked like shortly after planting the eelgrass in the top 2 frames. And what you're looking at in the bottom 2 frames are some of the images that we were able to collect over time at the donor sites. So you're looking at I think it's a school of Salima swimming around above the eelgrass in the lower left corner, and that is a bat ray off on the bottom right. Next slide, please. So here's a look at at some of our early data. Next slide. So when it came to the wave characterization, what we had seen, as is illustrated over on the left side of this frame, as higher wave height persisting at intervals in Santa Monica Bay in comparison to the donor sites on the backside of Catalina Island. So this is largely westerly swells that are sheltered due to the geography of Catalina Island. So we saw a little bit increased wave energy in those transplant sites than we had in the donor sites. And again, we were trying to come up with similar site characteristics to help assess whether or not we were getting it done. You see wave height and period also displayed on the right, and in that case you're looking at differences between sites, between transplant sites in Santa Monica Bay. So a few things to maybe look at, maybe the development of a trend or two especially in the period, the wave period persisting in those areas over, in that case, the summer. Next slide, please. Temperature. Here's plots for the benthic temperature off of Catalina Island in the left, and the benthic temperature during that same period of time over on the right. They're not, the time frames don't match up perfectly, but what we're looking at is a fairly happy range in temperature for this species, at least that we anticipate. Next slide, please. As I mentioned, we're looking at light, trying to make sure that we've got enough photosynthetically active radiation for these transplants to persist. These are data that were collected off of Catalina at the time that we were completing this grant. We didn't have the same number of PAR sensors out there in Santa Monica Bay. That work is continuing to develop. So we're looking at more sites we've acquired more sensors with the support of a few other folks in addition to this grant. And with that expanded effort, we hope to better characterize what's happening with light. Next slide. All right, that's the final one. And we had, so long story short, we had grass that persisted for more than 100 days after transplanting, which we considered to be a measured success for this work. As I had shared, we're continuing to monitor these sites and deploy sensors elsewhere in Southern California waters, largely in concert with Riley Sanders, who's working on his PhD at Scripps as part of this ongoing effort. He is becoming our grass guru for sure. And we'll continue to look at dissolved oxygen, temperature, wave characterization, and light to help us understand where we might find better site suitability for these types of transplants. And in the long run, if we can figure this out and it works, then we might be able to significantly expand the extent of these seagrass beds off of our coast to help us manage sea level rise, retain sediment, sequester carbon, and provide other habitat benefits and ecosystem services. Thanks so much.
Fantastic. Thank you, Tom. So now we're going to head into some Q&A and discussion. So Russell, if you could turn on your camera and your microphone, please. We have gotten a couple of questions in. All right. So first one, I'll pitch this one to Russell. This is from Marilyn, who is a colleague down in California. This is for you, Russell. Thank you. Really interesting work. Did you also get recruitment of native Olympia oysters? And did you consider seeding the Pacific oyster bare half shell with native oyster spat?
We tried it in our initial pilot study, which we began in 2014. And we seeded native oysters exactly as you suggest to see if that would work, because our preference would have been to promote Australurida, the native oyster. Unfortunately, they didn't grow fast enough, and they wouldn't grow in the shallow areas that were ideal from a geomorphological point of view for sediment trapping. They needed to be deeper down, and when we did grow them deeper down, they were entombed in the accumulating mud. So with great regret, we decided that if we were going to build living breakwaters, living shoals, we were going to have to work with the commercial oyster. At the same time, we are still working with shoreline landowners around the islands to see if there are any locations where we might be successful with native oysters. We do have a couple of locations where there were pre-European native oyster complexes that were maintained by indigenous people, and we have our eyes on them at this point.
Great, thank you. Okay, the next one, Tom, this one's for you. This is from Juliet. Is there any 2023 data that shows growth and success and biodiversity outcomes 2 years down the road? And then it says, I think the data that was shown for Catalina was all 2021. So I think she's curious as to what kind of the latest results are and, most recent data.
Yeah, no, very, very good. And sorry, I don't have the most up-to-date stuff to share. Riley's working that up as we speak. What I can share in addition to what I showed was that we don't have any survivorship from those transplant beds in Santa Monica Bay at this time. We're continuing to go there and continuing our quarterly surveys in case they do sprout up. I think as the clock continues, maybe we get less and less likelihood of that happening, as any of the energy stores in those rhizomes will diminish. That said, the other part that the data have shown from this past period that it didn't present today is that we had some dissolved oxygen issues in the site neighboring Redondo Beach, which is next to one of the mouth of one of our submarine canyons. So likely an internal wave type propagation coming up and bringing up low DO water. So we're increasing our interest in our approach to understanding that as well. As for the donor sites, which under our permits, we have to monitor as well to make sure we didn't cause any undue harm or damage to those. We've continued to conduct those surveys. One of those eelgrass beds is on the scale of close to 90 acres in expanse, and removing a few hundred turions from that has been de minimis. We've not been able to track any negative impacts from that effort. Thanks for the question.
Great, thank you. We have another one that came in from Angela. This is for Russell. Have you thought of using quar logs? I think that's how you say that, right? Quar logs for sediment to build up behind. If you're familiar with them, perhaps they're more shallow and can be planted with salt marsh plants. Have you thought about using those logs?
Yeah, I mean, one of the things that we wanted to do, though, was to maintain something that was very low cost and would be within the capacity of individual homeowners to do. So we were starting out with simple, locally available materials, things that were minimal tech and minimal cost. And so our approach was not to say what's the, let's say, the most effective way of trapping and redistributing sediments, but could we do this using just what we have there and then pass this technology on to ordinary homeowners, shoreline homeowners, and say, hey, you can do this too for about $10 a foot, which is about what it turned out to cost. So the short answer is no. But the reason is that part of the underlying philosophy of our program, which is a community-based laboratory, is we wanted to come up with a solution that we could then hand off to our community. And there are a number of neighboring homeowners now working on this and planning to plant their own shoals over the next few years. We put out a handbook, a manual, a video to go with it. We've held meetings with some of the neighbors. We even got the local marina to show some interest in building shoals around the docks to shield the bay from the marina activity. So all of that fed into the idea that we go simple, local, biodegradable, and if it works, great. If it didn't, then we had to go in for some better engineered materials.
And replicable, right? That was the
and
other
replicable.
thing.
Well,
Yeah,
yes,
so, yeah,
absolutely,
obviously, right?
easily replicable.
Exactly right. So, all right. So, Tom, I'm going to throw a question to you. So, you touched on this in your intro, and why? Wow, all kinds of questions coming in. But oh, actually, I'm going to switch this. Hang on, Tom. I'm going to switch it up.
I'm good. Go.
Tom had, this is from Scarlett. Tom had mentioned increased carbon sequestration through seagrass restoration. Do you know if there are any current initiatives to restore seagrass meadows for green carbon credit use? Which is a better question than I was going to ask anyway. So,
yeah, I'm certain there are. I'm not involved in any of them at this point in time. I think that there's far more studies of Zostra marina, better understanding for a lot of the biochemical properties and cycling of those beds. The big question for us with Zostra pacifica having a different niche, deeper, more open coast, would we expect to see that same sort of sediment drop out into the rhizomal mat, the increase in retention of organic material there? And so that's a question that we're continuing to inform. And once again, I have to credit Riley Sanders, who's working on his PhD at Scripps to help figure all this out. So more to come on that as to whether or not we can expect anything similar in the way of those sort of services from these Pacifica beds.
okay, that's a lovely intro to the question that I was going to ask, which is, investment in eelgrass. Like that was something that we had sort of touched on in prepping for this. So I would love to hear a little bit more about that in terms of the decision making on that front.
And did you want me to go after that one?
Yeah. That was you, Tom.
Okay.
Sorry, my bad.
No, that's perfectly fine. I'm thinking of the Salicornia peat in the back of my head.
Oh, sorry. No, eelgrass. Sorry, that was for you, Tom. My bad.
So Yeah, no, the way I think we looked at this, Susan, is that, 80% or so of the nearshore environment in Southern California is soft bottom habitat. We have anecdotal understanding that there used to be wider ranging, larger seagrass beds in the region. And for us, it's all publicly owned land. So I don't have to put it into conservancy. I don't have to purchase it. And following what Dr. Barsh was sharing, like the economics of this as a long-term practice are forefront in our minds. So we're trying to figure out the most cost-effective way to do this. And if we can, then we see all these benefits up and down our coast, which we'd love to see materialize to continue to promote a great quality of life for ourselves and for all those other denizens.
Okay, great. Just looking to see if any other, nope, I think we're good. So looking at the time, so I guess Russell, any last comments or remarks or quick things you forgot to mention or whatever you'd like to close on?
Well, since we're talking about economics and feasibilities, one of the things that we're dealing with in the Salmon Islands is that we do have divided public and private ownership. We have 17 different public landowners in the Salmon Islands, plus thousands of private landowners. And just around Fisherman Bay, which is about 2 miles of shoreline, we have over 100 homes and businesses that own shoreline, or in many cases own tidelands, because we're pre-statehood settled area that still has privately owned tidelands. So that the key for us is doing something that's so straightforward, that works so simply and is so cheap that we can convince people to do it themselves, because there's no practical way to do it as a big public project. And so we've completed about a little over 1,000 feet of shoals. That's 1,000 feet out of about 8,000 feet that would really save the bay. But the whole trick now is continuing to work on this and involving the community so that that other 7,000 feet is filled in by homeowners who are thinking, yeah, this is what I like to leave my kids.
Valid, very valid hope, in their house. So,
Yeah.
Tom, last remarks, comments, other things you'd like to add?
No, I don't think I've got much. I just wanted to thank you, Suzanne, and thank Rob for everything along the way of this grant and getting this work done. We've enjoyed doing it. I hope that we learn enough that it does become a viable mechanism for us to pursue. And I just appreciated learning from Russell today as well. So thanks for your presentation, sir. That was great stuff. And I hope we get together and do it again.
Yes, I think that needs to be a plan for sure. So thank you to you both, and for all your work. And it has been fantastic working with you and your partners on this grant. Special thanks to Rob for all of his cat herding on today's webinar. So and for the rest of you, and for those of you who asked questions, thank you very much. Many thanks for joining us. Please sign up for our newsletter and follow us on our social feeds. And if you haven't yet, that's important. That's the best way to hear about things like new grant opportunities and other things like that. So please don't hesitate to reach out if you have questions or would like more information. Thank you and enjoy the rest of your day.